Okay, so now that you've had a chance to see polar coordinates and how they work, we're actually going to try solving a problem, and you'll soon see the advantage of working in polar coordinates for some problems. Okay, so in this problem, you're given a wheel that's just rotating around at some fixed angular velocity um, omega. So remember, angular velocity is a derivative of the change in the angle of the wheel. So this is just spinning around at some rate. So it might be 1 second per revolution or 10 seconds per revolution. And then you have a bead which is released from the origin that can slide on one of the spokes, and you're told that it moves out at a constant rate u. So if we were to actually look at this over time, the bead might do some, it does some like kind of funny, kind of spirals out. You can imagine, like, because as the wheel is turning, it's going around, but also it's sliding out along the spoke. So it might look something like that. Okay, so how do we go about even solving this? How do we, or so, sorry, what's the problem? The problem is determine what the velocity is of the object. Okay, so we're going to do this first in polar coordinates, and then we're going to use that to determine what the Cartesian coordinates are. So in polar coordinates, so we've already told you that the r position relative to this, to the origin, is determined by how long it's been going and then the velocity it's going at. So it's going at a fixed rate u, and we'll go for some time t. So that's what all r is. Okay, so that's the radial distance. So actually the radial position will be ut in the r hat direction. So it might be, at some point it's here, or point here, but it's always in the direction that the r hat is the direction pointing from the origin to wherever it's at. So if it happens to be here, then the r hat will be that vector in that direction. Okay. So what else do we also know that this is the angular velocity. Okay, so from our previous discussion, we learned that v. Let me just switch colors yet again. So v in polar coordinates is r dot, so derivative of the radial position with respect to time, in the r hat direction, plus r times theta dot in the theta hat direction. Okay, so r dot is derivative of r with respect to time. So let's put that in. So that's going to be dr dt. Or let me actually just solve that separately. So r hat is equal to dr dt, which is equal to u. Okay. Theta dot we know is omega, and this is ut. So if we actually put that all together, we get velocity equals u in the r hat direction plus ut omega in the theta hat direction. Actually, so we're done. That actually wasn't so bad when you think about just breaking it down into, well, we know what how the bead moves along the spoke, and we know that it moves at some constant rate. So we're done. But now let's try to solve this using Cartesian coordinates. So remember that r hat is equal to cosine theta in the I hat plus sine theta in the j hat, and theta hat is equal to minus sine theta in the I hat plus cosine theta in the j hat. So if we actually plug all that in, we'll get the velocity equals u times cosine theta. I'm going to write this without actually writing out all the I hats and j hats, plus UTW times minus sine theta cosine theta. So that means that the velocity, yeah, I should have switched colors. I'll do that again right now. So velocity in Cartesian coordinates is going to be u cosine, and by the way, theta, actually we should put, theta is going to be equal to omega t, right? Because it's moving at a fixed rate omega, and then just over time, you know, if it's gone one revolution, then it's gone around t would be equal to 2 pi over omega. If it's gone 2 revolutions, it would be 4 pi over omega. So theta just determines, theta can be expressed in terms of time by taking omega, your fixed angular velocity, and multiplying it by time. Okay, so so velocity in Cartesian coordinates is cosine omega t plus ut omega. Actually, this should be a minus sine omega t. Okay, all of that in the I hat direction plus u sine omega t plus ut omega cosine omega t, all of that in the j hat direction. Okay, so that describes the motion of this bead moving on the spoke of a wheel that's just rotating around on a circle. Quite complex, right? But it worked. It's the correct solution. But this sort of says the power of just thinking about in polar coordinates and just writing it down. You're almost immediately able to write down the equation. When you switch to Cartesian, you have to do all this. You have to first do this trigonometry, and then you have to add all these components, and it gets complex. But you should be comfortable doing both. But this just sort of tells you the power of polar coordinates, and you'll soon see lots of applications that really make the setup of the problem much simpler in polar coordinates.